Okay, it's time to start. It's a pleasure to welcome Professor Tomaž Prosen, who came from Ljubljana, and who will speak about exactly solved models of many-body quantum chaos. And don't hesitate to ask questions, if possible, in the microphone.
Thank you. Yeah, thanks, Nalini. It's a pleasure to be here and to give a talk in this nice environment. So please ask questions also during the talk if something is not clear. So as you see, my title is slightly provocative. Yeah, exactly solved models of quantum many-body chaos. I mean, it should be somehow raising eyebrows because chaos is not supposed to be solvable. And well, you'll see what I mean. Okay, so basically, I mean, let me try to introduce or motivate the subject that I'm going to discuss in this slide. As probably in this audience, I mean, at least in mathematics of dynamical systems, people know simple models of chaos, right, which can be solved, like Baker maps or cat maps. And when I was learning many-body physics, I kind of missed this type of examples. I mean, it seems at first sight that many-body physics is much harder. That or quantum many-body systems. Quantum many-body systems are much harder. I mean, the models are either trivial or impossible, and there is no notion of chaos in the sense of exponential instability as in classical dynamical systems. So the idea is, and in particular, as you will see later, I mean, I will also try to ask questions about quantum chaos in terms of spectral statistics. I think this is very much related to this course. But we ask these questions about many-body dynamics, many-body systems. So the question is, I mean, are there some analogs of cat maps and Baker maps for quantum many-body systems? And of course, I wouldn't be giving this talk if the answer would not be a kind of yes. Namely, I will show you how to define or how to come up with models for which are complicated enough so that they have random matrix spectral statistics or exponentially decaying correlations, yet they are simple enough to be amenable to exact computations or even proofs. And that, I mean, at least I find it quite exciting, and yeah, that's the reason I decided to give this talk. But before going further, I mean, I have to emphasize these two heroes here who are responsible for this progress. Bruno Bertini was a postdoc with me since 2017 to 2020, and Pavel Kos at the same period made a PhD on the topic. So, yeah, so let me start with some motivation, but it should be quite clear. I mean, if you are attending this course, I guess this motivation should be clear, right? I mean, why? I mean, the idea is basically to have some understanding of this, what people call Buchigas-Giannoni-Schmidt conjecture or quantum chaos conjecture. I mean, it's basically the statement of correspondence between spectral statistics and chaoticity of the underlying classical dynamics. Yeah? Here is illustrated in terms of these simple billiards. Circular billiard is integrable. I mean, for this, actually, one applies a separate conjecture, which is called Berry-Tabor conjecture, usually, which implies that this type of systems, which are integrable, should have spectra given by Poisson sequence. So no correlations among levels, and that means that level spacings are, this is level spacing histogram, should be distributed like Poisson. But chaotic systems should have Wigner-Dyson or GOE, depending on the time reversal symmetry, GUE level spacings, for example. Okay, but you know, we'll try to do some rigorous statements. So we'll try to focus on something simpler. I mean, level spacings are too hard. So what people usually do, they consider pure point functions, like 2-point functions, like spectral form factor. And moreover, we'll focus exclusively on time-dependent, periodically time-dependent systems, the so-called Floquet systems, which conceptually to me are easier than Hamiltonian systems because there is no conserved quantity. And in Hamiltonian systems, there is conserved energy, so spectrum and spectral density can depend on energy, and things are harder. Here, I assume that my Hamiltonian is time-dependent, and the time dependence is periodic. So this is a one-period propagator. So this is the evolution operator, the propagator of the Schrödinger equation for one period of the drive. So this is a unitary operator, and its spectrum I denote as phi sub n. So this is the spectral density. It was somewhere in the board before. Now it's for a Floquet system. So spectral density now is defined on a unit circle. It's supported on a unit circle, right? Phi goes from 0 to 2 pi. And with respect to spectral density, you define two-point function. This is like a one-point function. You define two-point function with respect to the center of mass coordinate and the distance coordinate. So you integrate over the center of mass or center of the spectrum, midpoint, and then you get a function of the distance r of theta. I mean, basically what we define is a connected function, right? Connected correlation function. So we subtract the product of the averages, which is 1, because the average spectral density by construction, the way it's defined, 2 pi over n here, and this curly n is the number of levels, makes it 1. I mean, the spectral density is 1 on average. So this is the correlation function, two-point correlation function, or density correlation function, density correlation function. And then what you do is you take Fourier transform, right? And then you get what people call spectral form factor. So it's a two-line calculation. It's super simple calculation, which gives you this simple formula, right? So this spectral form factor is just double sum over the spectrum of these phases, e to the it and the difference of the levels. So these are like phases, and you see, I mean, from this you already see that there is something special about time scale, which is of the order of number of levels, because after this time, all these level distances get magnified by at least 2 pi. So which means that all these phases become pseudo-random. So after this time, quantum mechanics basically becomes almost periodic, pseudo-random evolution. Okay, so what is even more remarkable is that, you know, of course this is all very elementary, but still, I mean, this calculation is nice to do at least once. What is really remarkable is that this Fourier transform of the spectral density is basically just a trace of the propagator to power t modulo square, apart from this delta function at t equals 0. But remember, t is an integer. So this is basically the thing, right? So if you have some access to computation of traces of the propagator, modulo square, so it's like what in statistical physics you would call a two-replica calculation, because you need 2 copies, because you want to compute at some point an average, right? So now this is another thing which now comes into the game. This quantity, as people say, is not self-averaging, so it doesn't make any sense for a fixed dynamical system. One has to do some sort of ensemble averaging, so one has to define some probabilistic set of dynamical systems, and then average over this set. But this set can be arbitrary, as I will show you later. These sets in many body systems can be arbitrarily narrow. So, I mean, this expectation value can be, okay, I mean, we'll discuss it later, but you see, this is not really a problem, right? It's a technical problem to make these things well defined, but, you know, conceptually, it's not such a big problem to define the spectral form factor. Okay, so now what does random matrix theory tell us about spectral form factor? So now what we would like to do is we would like to find really simple dynamical systems, in our case many body dynamical systems, for which one can show that spectral form factor behaves like for random matrices. So that would be like the simplest proof of random matrix conjecture for a specific two-point function, right? Or for all two-point functions, because a spectral form factor basically gives any two-point function, right? Depending on how you define it. So now this is what the random matrix theory tells us. I mean, here the corresponding ensembles of random matrices are unitary ensembles, the Dyson's unitary ensembles, so unitary, orthogonal, or I skip symplectic one. But in case when you have time reversal symmetry, you should apply orthogonal ensemble. When there is no time reversal, then you should apply unitary ensemble. And then the difference is that once you get a linear ramp with factor 1, and when you have time reversal, you have linear ramp with factor 2. So what you get basically is a linear growth from a spectral form factor to a value which is roughly given by the number of levels. I mean, this is what was already explained before. When time becomes of the order of number of levels, then the spectral form factor also becomes of the order of number of levels, because these phases get pseudo-random. Okay, so now this is basically what random, I mean, of course, this one can compute this. There are methods. People have done this many decades ago. But this, of course, is a result which is characteristic for a random matrix, which is a structureless Hamiltonian or structureless evolution operator. No physics inside. So it's completely universal. Now, where is physics? Well, physics is usually considered to be in this short time scale, in the time scale before which random matrix or universal description of dynamics applies. So there is usually, when you look at the physical models, there is usually some non-universal feature, non-universal behavior, which then goes into the universal random matrix behavior and then continues universal. So there is a time scale of crossover between non-universal and universal regime, which is usually referred to as, in condensed matter physics, as tau-less time. In mathematics or quantum chaos, is probably referred to as Ehrenfest time. But it's the same thing. I mean, depends also on the context. I mean, this is usually when you have a semi-classical chaos, and this is usually when you have disordered metals. But again, physics is usually, related. Okay, so now, yeah, please.
You say what is CSE, the orange one?
Yeah, it's a symplectic, circular symplectic ensemble. I don't care about this at this talk, but just to know that there is another ensemble which you might care about, which happens when you have time reversal symmetry which squares to -1. So the anti-unitary symmetry to square to -1, which happens in physics when you have half-integer spins. Okay, so now I will just give you now one slight introduction into understanding of spectral form factor in semi-classical chaos. So for single particle problems where you have a classical limit, where you can more or less understand what's going on in the corresponding classical mechanics. And this was like a tour de force, I think, of quantum chaos of 1980s, 90s, and 2000s. I think it was one of the main problems, which was essentially successfully completed by the mid of 2000s, even though, as far as I know, there is no mathematical proofs. So I think this is still a challenge for mathematics, to have more rigorous control of these proofs. This is a physicist proof, let's say heuristic. It's a heuristic, but it's a very good heuristics, I believe. And this explains why spectral form factor behaves like random matrix theory tells you. For example, the first order, this is the ramp, which I showed here. The first order was already explained by Michael Berry in 1985 by the so-called diagonal approximation. So the idea is to write a spectral form factor as a double sum. First of all, the idea is to write trace of the propagator in terms of saddle point approximation to Feynman path integral. So solution of Schrödinger equation, the green function of Schrödinger equation can be written in terms of path integral. And in the limit of h bar going to 0, you can use saddle point or stationary phase approximation. And then you get basically sum over the classical orbits, periodic classical orbits. Each trace of u to the t is sum over the periodic classical orbits of period t. In this case, tau. Sorry for change of notation. Tau is now the period. So you sum over all periodic orbits which return exactly time tau. Each orbit is weighted by the action and the amplitude. And then there is a double sum because there is also trace of u to the t dagger, conjugate. So, I'm sorry, I'm using complex conjugation as star here. These are just amplitudes. And now, what Berry assumed is now that there is this cancellation of these terms in this double sum, which happens unless these two actions are exactly equal, which happens on the diagonal. So this is the so-called diagonal approximation. So the contribution was assumed to come only from terms where the two actions are the same, which is the sum of squares of the amplitudes. And then there is a factor of 2, which happens when you have time reversal, because when you have time reversal, then each orbit is paired not only by itself, but also by its time reversed partner, which might not be the same, but it has the same action. It's the same, but running movie backwards. So, right, so that's why you have this factor of 2, and that's why you have this slope 2 for systems with time reversal symmetry. So that's probably the essential heuristics. The rest is now coming. I don't want to go into detail here because that's just introduction or historical, let's say, remark. I'm not going to do that in my talk. So, this will have little relevance for what I'm going to say next. So I'm not going to go into detail, but just to tell you that there is a very nice heuristics which explains not only this first order, but explains basically all orders. If you expand spectral form factor into powers of t, then it explains order by order. Each fixed order is given by a diagram which involves a certain number of self-intersections of the orbit. And there is a cute combinatorics and diagrammatics which explains then this this expansion. Anyway, what I'm going to talk about here is rather about systems with no semi-classical limit. So systems where h bar, effective Planck constant, is essentially 1. These are systems of spin 1/2 or fermions. So these are typical, and then, and this is something which, again, I mean, I should probably share my amazement of this on this type of systems and results related to this type of systems, because, I mean, this is something that I kind of carry with myself for 20, 25 years now. And when I, attended conferences in the early 2000s and people spoke about quantum chaos in many body systems, I didn't know what they mean. What they mean, actually, yes, what they meant was that they see Wigner-Dyson level spacings. But then, usually people have this type of Hamiltonians where you have L particles, L fermions. This is for spinless. Well, this is again, maybe, I'm sorry to mathematicians, but this is a bit, again, physics notation. These are canonical anti-commuting variables. I mean, these are like fermions, right? So these are creation and annihilation fermionic operators, which means that you have L particles, 2 to the L dimensional Hilbert space. And Hamiltonian is given in terms of this matrix. And this matrix is very simple because these terms are usually referred to as hopping in physics, and these are termed as interaction. And all these terms have very little non-zero matrix elements. So now if you look at this, Hamiltonian is defined in 2 to the L dimensional Hilbert space. So Hilbert space is a tensor product. If you want, you can write it as L spins as well. So it's a tensor product of L two-dimensional Hilbert spaces, C2. Tensor product L times. And these guys have only of the order of log n, or L. L is, n is 2 to the L. So this is of the log n different matrix elements which connect two states. So you can only hop to a neighboring site, for example. And here you can only have overlap. I mean, these are only diagonal. But again, I mean, what you can say is that this is a matrix, it's a huge matrix, 2 to the L by 2 to the L, which is hugely sparse, which in each row has only of the order of log n non-zero elements. Moreover, this matrix is not random at all. It has only 4 possible values, or totally non-random, deterministic values. So now, I was puzzled by this question. I mean, how is it possible that these super sparse matrices can have...
So why are there, you said there are log L non-zero elements?
Yeah, of the order of log L, or 2 like 4 log L. I mean, depends, how many terms you have here. But each term results in, I mean, you can hop, you can change one particle. So you can, which means you can connect, each states are labeled by strings of zeros and ones, yeah? And 1 0, and one can hop. So it's like of the order of number of sites, particles that can hop. So it's log of the total Hilbert space dimension.
Okay, so
log of 2 to the L, so it's L. Yeah. It's L. Okay, it's fine. It's of the order of volume if you want, but volume is not the Hilbert space dimension now, right? I mean, this is, this is something that is very hard to embrace fully if you work with single particle problems, right? I mean, this is many body system. Hilbert space is a tensor product, and things scale exponentially. I mean, dimensionality scale exponentially. That's the hard thing about it. Anyway, but the matrix, that's why the matrix becomes super sparse in thermodynamic regime, let's say. And how can you explain that these super sparse non-random matrices eventually give random matrix spectral statistics? So this is the key problem which we would like to have some flavor of. Yeah. So, in physics community, I mean, people call this quantum chaos, and at least condensed matter community call this quantum chaos since early 1990s. Then there came progress or different ideas from high energy community, which call quantum chaos something else. But still, I mean, now I think now these views maybe are coming a little bit closer together. So, but maybe I can say a bit more on this at the end if there is time. But I mean, this is what I would like to understand. Let's say this is what we would like to understand a little bit during this.
But L is going to go to infinity.
L is going to go to infinity. Yes. I'll have thermodynamic limits, yes. And my statements will be true only in thermodynamic limits. So that's actually, that's probably the price I have to pay. that I'll be able to say something in thermodynamic limit only. And then you see how things go. But now let's start with some numerical experiment. So this is how it looks if you compute spectral form factor for a spin chain of L spins, where L, I think, is 19 or 18. I mean, it's a couple of 10,000 levels. And this is what you get. So this black sand is what you get if you ask your graduate student to compute spectral form factor. It makes no sense, right? It's not self-averaging, but it's very easy to self-average it. I mean, what you do is here, what we did is we didn't do any ensemble average. We just did a running time average, which means you just take 100 consequent time steps. Now time is an integer. Here we divide time by the Heisenberg time. So this is t to the 2 over L. Heisenberg time is 2 to the 2 over L. And also spectral form factor, which we call here K2, is scaled by 2 to L. So it goes from 0 to 1. And you see, I mean, when you do moving time averages, then things become kind of regular, right? This black curve is a moving time average, and then you compare it to random matrix, and it's beautifully agreeing. So this is just some numerics to show you that things actually work.
And so what are the black dots everywhere?
Black dots are everywhere are numerical results for spectral form factor, which you get from definition. Let's say if you compute.
And when you average, you see that they are concentrating around this.
Oh no, these things are not. Sorry. Oops, what did I do now? Oops, something froze. No, okay. Sorry, what did you ask?
So when you compute individual values, you get this black dot.
Yes, yes.
And then you average over small time intervals.
Exactly.
Exactly.
Yeah. Yeah. Just to show that it's not needed to make, that this definition of spectral form factor, which is in terms of ensemble averaging, is not really needed to average over a model parameter. It's enough a moving time average. But okay, I mean, it's just some empirical statement. Okay, so now I believe that only very recently the first kind of results appeared which kind of explained why these quantum spin systems of many interacting spins can have statistics related to random matrix theory. There was a couple of papers, let's say 5 years ago, one from our group and two from a group in Oxford from John Joker and his collaborators, related to working on slightly different paradigms. I mean, and I don't want to go into either of the two, because neither of them satisfies me yet, I mean, for the purpose of my talk. Here, John Joker had to take large local Hilbert space dimension, which I'm not happy with because it means small effective H bar. And what we had to take long-range interactions. And this also is not fully satisfactory, at least not for what I'm going to want to do next. I really want to have local interactions because these are kind of, I mean, the most structured model, most low-dimensional model, and probably the hardest to understand.
So large local Hilbert space would mean, for instance, let the spin go to infinity?
Let the spin go into infinity, yes. But then, of course, it's not really a semi-classical limit because then they take random gates. So it's a kind of effective random matrix model. It's a structured random matrix model, if you want, what they have. So they have local matrices, Q square by Q square, and then they place them, then they act on tensor product CQ, so the space is on this Hilbert space. Okay, so now what I will really speak about is spin 1/2 systems with strictly local interactions. And the simple paradigmatic model, which I'm going to start with, is what we call Kick-Teasing model. So it's probably the simplest, at least in terms of physics, the simplest model that we can think of. It's also, well, I don't want to, but it's a simple model, which, you know, people usually call this Ising model. So it has two interacting spins, spin 1/2s. If you want, these sigma matrices have eigenvalues +1, -1. So these are diagonal Pauli matrices at different places. So this is, again, tensor product notation. So this J means that it acts non-trivially on the jth copy of tensor product. And then there is external field, a longitudinal field, which can depend on position. And then you kick this this is essentially classical Ising model because it's diagonal. I mean, the Hamiltonian is a diagonal matrix. But then you kick it, which means you pulse, you switch on and off in pulsed way, periodically, interaction, which, well, I mean, kick, which is the transverse field. So it's like, I mean, the Floquet propagator is now kind of a two-pulse protocol, right? You first take the Ising Hamiltonian, and then in the next time step, or in the next part of the time step, you take kick, and then Ising and kick, and so on and so forth. So it's basically the simplest Floquet operator you can imagine. These guys do not commute, so it's really quantum model, right? You cannot write it again. I mean, and also it's Floquet. I mean, it's not Hamiltonian because there is no Floquet Hamiltonian in general. What people call Floquet Hamiltonian would be that you would write this as an exponential of a simple local Hamiltonian. Now, this model has basically two key parameters, which is the spin coupling, J, and transverse field B. And it has this position-dependent longitudinal field. And this will be my disorder. This will be my averaging parameter, as you will see. So this model is integrable in two trivial cases. Either if transverse field is 0, then it's just classical, 1D Ising model, obviously integrable. You can write partition sum exactly. It's a textbook example. Or when there is no longitudinal field, when there is purely transverse field, this model is also integrable, slightly less trivial integrable because it has to be transformed using Bogoliubov transformation to free fermions. But for generic values of H and B, this model has no symmetries and it's not integrable. So now, what we will do with this order, I mean, how we will define spectral form factor. So now what we will do is we will take this longitudinal field as IID random variables, which will be Gaussian distributed with mean H prime, H bar, and variance sigma, or sigma, standard deviation sigma, so sigma prime, sigma square variance. So, I mean, this is just a multiple Gaussian integral if you want. So what we want now is to have a method of computing the average spectral form factor averaged over these random fields. And why is this? I mean, I want to claim that this is very innocent averaging, in particular, since our result will be kind of insensitive to the magnitude of the noise. So, I mean, they will be the same if you take the limit of noise going to 0, so variance of the noise going to 0 at the end of calculation. So they will be also true in the 0 disorder limit, let's say. But the point is that you would have to have some non-zero disorder in order to claim the results. So what is the result? Well, this is, again, just some numerics to motivate the result. So for J is equal to B is equal to pi over 4. So these are special values of these parameters, which we call a self-dual point. I will explain later what I mean by that. But at some particular value, which is kind of the hardest, in some sense the hardest, the most non-integrable, let's say, the farthest away from integrable points, with J and B is pi over 2, pi over 4, which means, this is like, this is operator with integer spectrum. So if this J is a multiple of 2 pi, it doesn't do anything, right? Also, if it's multiple of pi, it's just a sign. So if it's multiple of pi over 4, it's the hardest. I mean, it's halfway between trivial limits. Okay, so now, this is what you get. This is what you get when you compute spectral form factor. You get a linear ramp. This is for 15 particles. So Heisenberg time is 32,000, somewhere the next building. So here you expect a perfectly linear ramp, and this is what you get. Now, for very small times, you get large fluctuations, but it turns out that these fluctuations get smaller when you increase the system size. So when you increase the system size, this fluctuation gets smaller. So it seems that numerics suggest that there is basically perfect agreement with random matrix spectral form factor. And this is indeed the case. So this is actually the theorem which we can prove. In thermodynamic limit, we can prove that the spectral form factor is equal to 2t for odd times for times larger or equal 7. And 2t minus 1 for times less or equal 5. So there is a simple finite time fluke. But apart from these very short times, spectral form factor exactly matches to t, which is a random matrix result in thermodynamic limit. So now in thermodynamic limit, of course, Heisenberg time goes to infinity, so linear ramp should extend to infinity. So it's basically just that. Now, there is some issues, and one issue is that we have to assume the time is odd. So there is some technicalities I don't want to go into here, but because I'm going to say something much simpler in the next couple of slides. But this model is still, I mean, I think it's the first model and the most simple to motivate. So it's probably good to stress this result. But it's in that sense, I mean, this model has time reversal symmetry, so there is a factor of 2. You can understand this time reversal symmetry.
So can you explain again why you don't worry about this -1? T -1?
Say again? What?
You said, I mean, instead of 2t, you have 2t -1?
Yeah.
It doesn't matter? Or?
Well, it doesn't matter because anyway, there has to be some tau-less time, right? Because for very short times, we usually expect that physics should be model dependent. And here this is really, I think, I mean, usually what we get is a tau-less time which grows with log h bar or log L, for example. I mean, it grows with growing the system. So here we have a time 5, which doesn't change. So it is there in thermodynamic limit. So I think it's totally innocent, right? It's a finite time. Yeah. But now, you see, I mean, for even times, there is something, we can only make a conjecture because the algebra gets too difficult. And then what the conjecture is that for times larger than 12, this is 2t plus 1. And we understand this one. But I don't want to get into this, but because I want to share, I mean, to spend the rest half of my talk to present these results in a much simpler context, at least technically simpler context. Maybe in terms of physics is more subtle, more complicated, but in terms of mathematics is simpler. So I would prefer to go further. And yeah, so, but let just me conclude. I mean, what I already stressed, I stress again. The results are independent of sigma, as long as sigma is positive. So the model is ergodic, quantum chaotic, for any disorder strength, which means that it excludes the so-called Floquet many-body localization in this model. And in particular, we can take the limit of the clean system limit at the end of calculation. Yeah. And the results are also independent of the average longitudinal field. So we can even take average longitudinal field equal to 0, which corresponds to a limit of the integrable system. So we can take a kind of disordered perturbation of the integrable system. If you take thermodynamic limit first and then disorder to 0 limit second, then the result doesn't change. Okay, now, so just one slide to motivate how we approach this computation. Basically, the idea is to map this problem to a statistical mechanical problem. That is to map computation of a trace of the propagator to a partition sum of a 2D statistical model. And in this case, this 2D statistical model is exactly 2D Ising model in random field. So it's not an integrable system, because you know 2D Ising model is integrable only when there is no external field. Here there is a random field, random in space, but uniform in time. So these two axes are time and space. So field is random in space, but constant in time. Yeah? And now when you change, then you use this so-called duality transformation, when you, that you evaluate the trace. Rather than using transfer matrix in time, which is called propagator, you use transfer matrix in space. And what happens in these particular values, j is equal to b is equal to pi over 4, then this matrix becomes, I mean, this is what we call self-dual points. And why is this so cool? Is because this dual transfer matrix becomes unitary. So the propagator for quantum dynamics is a unitary operator. But now in this case, also the transverse propagator which maps spatial configuration at fixed time, temporal configuration at fixed space to another temporal configuration at another spatial point. So this row transfer matrix. This guy is also unitary, and this guy is also unitary only at these particular values. And this is something instrumental for our computation or for our proof of the statement I told you about earlier. Okay, but now as I say, I wanted to kind of explain this result, but you know, it would be probably too challenging to do it in one lecture for Kick-Teasing model. So I'm going to do it for a much more general class of models, for which it's easier to present result, but also it's a more general class, so maybe it's even nicer. But it's kind of what is more difficult about this is, of course, that it's more maybe more less physics. Let's say less physicsy. So what is it? I mean, this is what we termed dual-unitarity. So it's about quantum. I mean, this is like again constructing Floquet dynamical systems, discrete time dynamical systems, many-body dynamical systems, but now kind of abstract dynamical systems in terms of gates, in terms of two qubit gates. I mean, now we can have qubits. I mean, here I assume this was Q. Now I assume this is D. D is local Hilbert space dimension. So what I have now is a 2-on-2 unitary map, which now maps states I and J to states K and L. So this for me is a propagator, right? And I did designate this map in terms of a box, which has 2 in and 2 out legs. Yeah? I don't even put any arrows because it turns out it doesn't matter. But you can assume that this unitary acts in this way, so bottom up. But then you can define what we call a reshuffled basis or reshuffled gate. So we define a gate we define this reshuffling operation, such that we define a reshuffled gate which we denote as U tilde. And this gate applies, basically this gate maps states I and K to states J and L. It's just reshuffling of matrix elements. Now there is no reason why this reshuffled gate would be unitary, but it can happen. And if it does happen, then we call this gate dual unitary. So a gate which is unitary in 2 perpendicular directions, so the gate itself and the reshuffled gate is unitary, we call a dual unitary matrix or dual unitary transformation. Now, actually, this is actually not just something out of the blue. I mean, this is actually related to classification or I mean, it's basically in one-to-one correspondence to unital maps in quantum information theory. So, and the problem of classification or parametrization of these dual unitaries, as you will see, I will stress later, but is a hard problem except for d equal to 2. For d equal to 2, we can completely solve it, but for d larger than 2, it's still unknown how to present the most general classification of these dual unitary gates. But so we don't care about this now. I mean, you see we have rich sets of examples. So let's just assume we have a dual unitary gate. Now let's form dynamics, many body dynamics out of it. So what we do is just that we kind of fill the plane with this. I mean, we make this so-called brickwork circuit. So we take an even number of quantum spins, or d spins if you want, d-level spins. And then this gate applies to first pair 1, 2, 3, 4, and so on. And then we shift the array. So it applies to here to even pairs, here to odd pairs, even pairs, and so on. So we form a unitary dynamics, which is a product of what we call even and odd step. So it's a level, it's two levels, two temporal levels. And then we basically map, iterate this dynamics t times. So we call this now two steps. For example, this is 1/2 step, second half step, and this is a full-time step, and this is twice full-time step. Now, we can also define what we call a dual propagator, which is now going this way. Now, time goes vertically now, and so time usually goes this way. And now space goes perpendicular, so now we can also define this as a propagator U tilde, which maps like four spins in time direction along space direction. Yeah? And now we have this clear identity of traces. So you can define this partition sum with periodic boundary conditions in space and time, and the partition sum is given either as trace of u to the t or trace of u tilde to the l. Okay, so now this is just to motivate, right? So now we have, I mean, you can also call this quantum cellular automaton. I mean, this is, for people who do cellular automata, this is a quantum cellular automaton. It maps local operators, it maps local operators or local observables to local observables. For example, I mean, if you, well, I will discuss it later, maybe, but yeah. Okay, so now let me just spend 1 or 2 minutes on presenting the complete classification of dual unitary gates for qubits. So we can do this for qubits, which means d equal to 2. For d equal to 2, we have this nice formula, which has some name, but I forgot. There's a nice formula which allows you to parameterize completely a matrix, which is SU4 or U4 matrix. So d equal to 2 means U is a 4×4 unitary matrix, and you can decompose it into a product of 2 SU2s, so-called Heisenberg matrix, and another product, tensor product of 2 SU2s. So this U plus, U minus, V plus, V minus are arbitrary SU2s, and this is a Heisenberg gate, where here you have JX, JY, and JZ. Now, here I put some other values, but suppose you have arbitrary JX, JY, JZ, so you have 3 plus 3 plus 3 plus 3 plus 3, which is 15, plus 1, which is 16, which is 4 square, real parameters which fill the manifold of U4. Now, you can restrict 2 out of these 16 parameters to pi over 4. And then it happens, then you have basically codimension 2 submanifold in manifold of unitary groups size 4. And then basically what you can show is then this map becomes, this matrix becomes dual unitary. So it's now unitary under this duality reshuffling. So it's just 2 parameters you have to fine tune in order to get a dual unitary transformation. And examples are what is called a swap gate or XXZ gate, which is integrable, or what I discussed earlier, this self-dual Kick-Teasing model can also be written as a quantum circuit, and there is this particular decomposition of the of the 2-qubit gate. I mean, it looks horrible, but you know, it's just the way to write what we wrote earlier as a simple physics model in terms of this abstract quantum circuit. And let me just stress, I mean, this is of course not so abstract, because now we live in the area of NISQ devices, and there are groups around the world where people can easily simulate this on a quantum simulator, or if you want to call it quantum computer. For example, this model has actually been simulated already 2 years ago on a Honeywell quantum computer. And they used these results that I'm going to discuss later on in my talk, they used them as a benchmark for a quantum simulator. So it's nice to have chaotic quantum system, which is exactly solvable, because you can benchmark your quantum computer, for example. That's, if you know, maybe for mathematicians, it's not so important to have applications, but you know, if you want to discuss, if you want to convince your physics friends, I mean, it's much more important, right? But anyway. Okay, so now let me just discuss once more spectral form factor. So now let me just illustrate the most general result we can write at the moment for a class of circuits, for a much more general class of circuits, for which we can prove random matrix level correlations. So this class of circuits would be the following. Suppose you take one layer of this, again, I'm going slightly back, so now we are just making a bit more structure on this brickwork circuit. So what we do now, we take a brickwork circuit where we have 2 layers. I mean, this is like 1 time step, 2 half layers. And these 2 half layers are composed of dual unitary gates, these different shades of red. I don't see it very clearly here, but you should probably imagine that these are different shades of red, meaning that these are 2 different 4x4 dual unitary matrices. And then these matrices are dressed, or they are connected with these circles, and these circles are local unitaries. I mean, this is this tensor network notation that people in quantum information and quantum optics now like very much, and also we like it very much. It's a very compact notation to write products of tensors, right? So now this you can think of is a tensor, right? Because it's written in tensor product space. It's a tensor representation of a 2 to the L or D to the L by D to the L unitary matrix, and it's composed like in terms of Lego cubes, and each Lego cube is something like that, right? It's a big piece which is constant, and there are these circles which is like product of this is exactly this. This is a red cube, and now this is like a tensor product of two SU2s, which apply on two different legs, yeah, right? So now this is this beast, right? And then you take one layer and the second layer, and you repeat, right? The point is now that these circles can be all different, which means that you can have disorder. I mean, you can have a disordered field. I mean, these circuits, for example, for qubits means you have a random magnetic field, because arbitrary SU2 can be generated by exponential of some vector times vector of Pauli matrices, right? And so this vector has a physical meaning of magnetic field. So it's like a spin chain in a random magnetic field. But now the distribution of these random fields could be arbitrary. It turns out that it can be arbitrary distribution, no matter, arbitrary narrowly supported, if you want. So it's really just a technical trick how to make this calculation through. Okay, so now what do we do now? We compute spectral form factor, which is like a partition sum of 2T by L lattice. So it's L time steps, T time steps, L spatial dimension. And now what we do, we write it like this, like expectation value with respect to this U is value of the field, right? So these are these single qubit unitaries, small unitaries, these blue circles. And then we average over those. But before doing that, we replace, first of all, we use this identity, the trace of the square, product of traces is trace of the tensor product. And then what we do now, we use this space-time duality, which means that we replace this propagator u with propagator u tilde. Now let's do this. Now I try to just convince you a little bit that it's really useful to draw pictures and tensor network diagrams. So basically what we do is essentially, I'm just repeating this calculation now with pictures, right? So now what we do is basically we write tensor product as a expectation value of 2 replica calculation. And this is just this. This is one replica, the other replica. Everything is periodic boundary conditions in space and in time. That's why it's trace. And it's power t, which means there are t levels. So this, here t would be 3, 1, 2, 3 levels. And space would be 1, 2, 3, 4, 5. So this would be 3 by 5. And now, what we do now is basically we do the folding. Why do we do the folding? Because we don't want to have 2 replicas. We just put one on stack on top of the other. But then what we do now is remember, disorder was constant in time, but different in space. So now, before we contracted this vertically, but now we'll contract it horizontally, which means that disorder now factorizes, because disorder is now different at different points in space. But it's the same at different points in time. So which means that now we can evaluate the disorder average locally, point by point. So basically we replace this expectation value by local expectation value. So which means that now, oops, I'm too fast now. So which means that you can write everything like, the end result, like some transfer matrix, which are called doubled t, to power, in this case, 1, 2, 3, 4, 5. So this is, So this is like trace of t to the L, t to the 5 in this case. So now the point of the goal of the game becomes controlling the spectrum of this transfer matrix, because now we'll go to thermodynamic limit, and then we'll ask what happens to the spectrum in thermodynamic. What happens to this in thermodynamic limit, which means we'll have to control the part of the spectrum on the unit circle and the gap with respect to the rest of the support. Now this is, first of all, now this dual unitarity becomes very important, because dual unitarity guarantees that this u tilde is unitary, and composed with the averaging, this becomes a non-expanding map. So this map should have a spectrum confined within unit disk. I should not go into any detail. Let me just state the theorem which we can prove. So it's kind of funny. I'm happy that I can somehow try to explain this to mathematicians, let's say, or more mathematical community, because to me it's kind of fascinating that we get the result which is kind of similar to what people find in semi-classical chaos, but the mathematics is completely different. The algebra, now it's all about algebra. Now it's all about operator algebras. So the idea is basically to map a computation of spectral form factor to counting the dimensionality of a commutant of some simple set of operators. And these operators are really simple. These operators are defined on a time lattice, so on lattice of t-spins, or 2 t-spins, but it's staggered. And there is some natural staggering, as you see here. There is this even-odd effect. But it's 2 t-spins, so vertical lattice. So now we have this operator, which is like magnetizations on time lattice and magnetic spin interactions on time lattice. And what we want to find is the commutant of this set spanned by this operator, which means we want to find the maximal set of operators which simultaneously commute with these guys. And it's easy to find these operators. These are translations. These are just t translations. The question is, can we show that these are all operators that there are, right? So the lower bound of spectral form factor is trivial, is t. But what we claim is that not only the lower bound, it is saturated. So this is the kind of the heart of the proof, is basically to struggle with this and to use representation theory somehow to find that there can be no other operator which simultaneously compute with these guys. But it's really just purely algebraic problem, so it's completely different maths, I would say. Okay, so now, yeah, I should probably close in 10 minutes, so let me just give you something else. Maybe there is some question here. It's probably good to make a pause if there is any question. Because now I'm going to change gears and I'm going to go less into details, but more into what we can do with these models.
A question, is there any chaos somewhere, or is just that the result looks like?
Well, to me, chaos is in random matrix theory.
Okay.
Yeah. There is no chaos, really, because there's no trajectories. There is no, I don't think there is, I mean, there is chaos only when you have correspondence principle. So that's, yeah. I don't know. That's why, I mean, when I discuss with my high energy colleagues, I mean, it's always this question because they like to have chaos. They have Lyapunov exponents, but they also have large N theories. I mean, in holography, they have large N theories, and that's why they can have this Baldacina bound, and they speak about there is a real chaos there. But in spin 1/2 systems, there is no real chaos. There is just correlated spectrum, let's say. Correlated spectrum, or, I mean, it's not only about spectrum. And now I'm going to go really to time evolution of observables. You see that observables decay exponentially, so there is mixing. Maybe that's the best way to characterize it. There's dynamical mixing. And maybe one can make this more rigorous. I mean, that these models are mixing, but they cannot have. But then there is a question about dynamical entropy, right? We could discuss this also, but I don't want to extend this. I mean, for example, you can define Kolmogorov, you can define a non-abelian version of Kolmogorov entropy, like CNT entropy or Alitsky-Fanes entropies. I mean, there are proposals. But these proposals are not very, I would say, not very deep in the sense that they give trivial results, even for free systems, right? I mean, trivial. I mean, they give results like free systems are chaotic. They have positive dynamical entropy, which is clear, which is obvious because they are infinite volume. So they pump information from infinity of initial condition, and then they pump it into dynamics. So it's very hard to really come up with really definition of chaos in many body systems. So I prefer just to stay with what we can calculate and compare to random matrices. Anyway, so now, for example, in these models, what we can do also is we can compute completely general local correlator, which means we take two observables, and I just take all possible observables which are traceless operators, which are localized, which are local at, let's say, point X and Y, and this alpha beta labels indices from 1 to d squared minus 1. A0 is identity matrix, and these all other are, let's say, if you want, generalized Gell-Mann matrices, so traceless matrices. And what we can do now is we can formulate a tensor network prescription, the grammatic prescription to compute this arbitrary two-point function, dynamical two-point function of local operators. So this is just a Heisenberg picture if you want. I mean, and I don't want to go into any detail, but what you can do at the end of the day, you can find that this correlator is non-zero only when two operators are placed exactly along the light ray. Otherwise, it vanishes. So this is the only diagram which survives when these two operators are along the light ray. And that's kind of easy to understand because this dynamics is unitary in time, but it's unitary in space. And this unitarity also implies what physicists would call causality, which means that correlations can only propagate within light cone, right? And because this is a cellular automaton, so cellular automaton maps local things to local things. And support can only spread by 1 in 1 time step. So information can never propagate faster than speed 1. But now information can spread also in space direction, not only in time direction. So the intersection of cones which open in time and in space is just the light ray. So this is the only direction in which information can propagate. Okay, so now there comes connection to open quantum systems and quantum channels, or unital quantum maps, which I mentioned earlier. So now, this correlation function actually can be computed by iterating a quantum channel. So this is a correlation function of a unitary closed many-body quantum system, which is now equivalent to iterating a quantum channel, or of a single qubit, or single qubit. So it's like a perfectly Markovian dynamics, where many-body environment, so you isolate your target particle, and you treat the rest of the system as a Markovian environment. It's a perfect approximation. It's not only an approximation, it's a perfect situation in which the rest of the system acts as a perfect Markovian bath. I mean, this is something that some people dream about, when they want examples of Markovian baths. Now here, system really acts as a Markovian bath. This is something that you usually explain that, in chaotic systems with a chaos assumption, the system should somehow be kind of self-induced bath, right? This is, in these dual unitary circuits, this is like what happens, yeah? So this is my point. Okay, so now, then you can classify, for example, a type of correlation decays. You can go to textbook on dynamical systems, and you can provide corresponding ergodic hierarchy. For example, you can have mixing, ergodic and non-mixing dynamics, non-ergodic and non-mixing, and so on and so forth, depending on the spectrum of these quantum channels. Anyway, so now what you can do is you can also compute solve quantum quench problem. Probably I will not, it's probably better not to overburden you with too many things, but it just, to tell you that we can, take also different initial states, not any initial state, but the state which is so-called solvable initial state, and then we can compute local observables as a function of time, again using similar technology. We can compute entanglement dynamics, sort of any entropies of states or local operators. We can, well, the last thing which I maybe wanted to flash through, but I probably don't have enough time. So, but I just want to motivate the question. So the last thing, which was also the number 3 point on my motivation slide in the beginning, was structural stability. So as you know, I mean, in study of chaos, structural stability is a very important notion. So people believe that ideally chaotic systems like uniformly hyperbolic systems are structurally stable. So, and now when you go to quantum many-body world, I mean, you should probably expect something similar. I mean, if the model is chaotic, this should be maybe also one of the characterizing features of chaos, right? That it should be stable under perturbations, in some sense. So now we found some particular class of chaotic systems which are fine-tuned, but they are idealistic. I mean, they are ideal, so they have very nice properties. And now what we want to understand if they are structurally stable. So if they are stable under small perturbations. And we have some positive result in this direction, but it's a rather limited result, so it probably would take me at least 10-15 minutes to explain it. So probably I'm going to skip this, just to tell you that I'm happy to explain to anyone who's interested later. But there is something like a something like a convergent perturbation series around dual unitary circuits. Okay, so and then I would just like to close. So the point of my talk is that I presented what I believe are the first results on spectral statistics of extended quantum lattice systems when thermodynamic limit is taken first. And you see, I'm not feeling very well about this assumption. I mean, this is, of course, something you have to do in order to get some first results. But I would like to leave this assumption at some point. I mean, I would not like to be able to do things also by not taking thermodynamic limit first. And it turns out this is much harder. But why do we want to do that? For example, we want to have exact results in finite systems. We want to know how things scale by, for example, if you want to look at matrix elements of finite systems and statistics of matrix elements in finite systems, matrix elements by definition are defined at infinite time, right? So because it's a stationary problem. So we have to be able to take time to infinite limit first. But this is kind of not working yet with our methodology. So this is something that I would really like to see. And the big goal, which would be lying behind this, would be that dual unitary circuits might be models where ETH, eigenstate thermalization hypothesis, could be proven. But that's, of course, now a fantasy. And I would like to see it realized someday, but it's, yeah. With this, I would like to close, and thanks for your attention.